Okay. Today I will discuss two important identities in multi-rate signal processing. These are called Nobel identities. There are two Nobel identities. A, suppose there is a sequence x n, it is passing through a filter which is not h z but h z to the power m, which means there is an original h z in time domain small h n that is expanded by m. So, transfer function becomes h z to the power m, expanded means between every pair of samples m minus 1 zeros were placed, m is greater than or equal to 2, that kind of filter. And after this filter, if I suppose have a decimator by the same factor m, okay, let us call it y n and let us call it v n, then the claim is this is equivalent to first you decimate, then pass it through a filter not h z to the power m, but h this, you will get the same y n. Okay. This is the claim, this is the Nobel identity type 1. But before I give a proof, see the advantage of this structure. Here h z to the power m. So, between every pair of samples, say h 0, h 1, there are m minus 1 zeros. So, this is one sampling point, this is another sampling point, this is another sampling point. So, clock period is, if total is tau, it is tau by m. So, clock is high. So, this filter and therefore, the input is working at the same clock, okay, at as that of this filter. So, x of 0 comes, x of 1 comes, x of 2 comes, x of 3 comes like that. So, this system is working at a high speed. So, it is costly and then you are decimating. So, this is a low speed sequence, its period is tau, but here x n and h z to the power m, their clock period is tau by m. So, they are operating at a high speed and therefore, this system is costly. But see the equivalent system, x n was as before, its period was tau by m, but first I am decimating it. So, it is becoming slow, its period is becoming just tau, and then sorry, this is h z, I am very sorry, this is h z, and then you are passing it through the normal filter, it is h z. H z means original filter. So, h 0, h 1, h 2 gap is tau. So, this will be a filter working at a lower clock because it is after decimation. So, this will be less costly. So, by this process you can convert a costlier section into a cheaper section. Now, I have to prove it. Now, you see y n is decimated version of v n. That means, if there is a sequence v n, say v 0, then you have got v 1, v 2 dot 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 v m minus 1, and after that you have got v m, then again intermediate samples, there are 2 m, at 2 m you have v 2 m, then at minus m you have got v minus m dot 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 dot. This is v n sequence. After you decimate, you get y n. But what is y n? Y 0 will be v 0, y 1 will be mth guy here, y 2 will be 2 mth guy, y minus 1 will be minus mth guy. So, it will be at 0th point, it will be v 0 coming, at point number 1 v m coming, at point number minus 1 v minus m coming. That means, nth point will be v n into m, n is 0. So, v 0, so at n equal to 0 v 0, n equal to 1 v m, so at n equal to 1 v m, like that. Okay. That is what I am saying. 0 is sample, then mth is first, 2 mth is second, 3 mth is third, n mth is nth, all right. So, this is your y n. So, I have to find out y n here. So, y n is nothing but this v n downsampled or decimated. So, y n is after decimation of v n is this sequence. So, general sample of this sequence is what I have at nth point. Nth point I have got v n m. Okay, that is a general sample, that is V m, V 2 m, V 3 m, V n m. Okay. So, what is V n m? Let us find out. But before that, what is V n? Right. Remember, out of V n, I am not interested in all these points. I am only interested in either here or here or here or here. That is n mth points. Okay. Because n mth sample becomes nth sample. N mth sample becomes nth. 1 into mth becomes first, 2 into mth becomes second, like that. So, that is why n into m, that is important for me, because only they come in the yn sequence, right. But then consider this filter. This is a convolution between x n and h z to the power m. But what is h, if you call this filter as h expanded version, right, h e z, which is h z to the power m. So, what is impulse response of this filter? I am calling it expanded form. So, h e z. So, originally there was an h n, then expanded. Originally there was an h n, h 0, h 1, h 2 dot dot dot. It has a z transform capital H z. Okay. That is h 0, h 1, h 2 dot 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 dot. This had a z transform H z. Now, we expanded it here. You have got say h minus 1, you expand it. So, this is 0, this is h 0, h 1, but you have got m minus 1 zeros, then again m minus 1 zeros, then I have got h 2 dot 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 dot. This sequence is the expanded sequence, and I call it h e n, expanded version of this. It has a z transform h e z. What is h e z? We have yesterday seen it is h z, but not z, h z to the power m. So, this h z to the power m is called h e z. Its impulse response is h e n, which is the expanded version of this original h n. So, you can draw it like this. H e n means first we will have a 0, then you have got zeros, then mth sample is h 1, then again you have got m minus 1, h 2. Okay. In general, n mth will be h n, n minus 1 m will be h n minus 1, n plus 1 m. So, there are zeros in between, all m minus 1 zeros. This will be h n plus 1 dot 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 dot. This is the expanded version. Okay. With this I have to convolve x n. So, how to convolve x n graphically? This is a linear convolution. I hold h sequence as it is, flip the x n sequence. Okay. I flip the x n sequence, and I am interested in finding out output not at any arbitrary point, but n times m. So, either capital M or 2 m or 3 m, like that, because n m, n mth here will be nth here. Okay. This is y n. So, y n at nth point is v at n mth point. So, n mth points are of interest, that is mth, 2 mth, 3 mth, like that. So, I am interested in the general n m. So, I want to find out the output at n m, that is here. So, what I have to do? How to calculate convolution? I hold this h sequence as it is, flip the other sequence. So, x 0, x 1, x 2, x 3 dot dot dot, and x minus 1, minus 2, minus 3 dot dot dot, and this I shift by n m. If I shift, since you know graphical convolution, at n mth point will come x 0. Then I have got x 1 dot 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 x. Then again at n minus 1 into m, at this point will be who? X m, because I have got capital M minus 1 zeros. So, capital M minus 1 points here, x 1, x 2 up to x m minus 1. This is x. So, x0, x1, x2 up to xm minus 1, they meet zeros from here because m minus 1 zeros. Then at n minus 1 into m, okay, at n minus 1 into m, who comes? N minus 1 into m, mth guy, because at nm x0 has come, it is flipped. So, x1 was earlier to the right, it has come to the left, then x2, then x3, how many points? First m minus 1 points correspond to m minus 1 zeros, then one more point. So, that point is n minus 1 into m, that is nm minus m. So, there xm comes, then again some samples, I do not care. Then at again this point, next point, suppose n minus 2 into m, who comes? X 2m dot 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 dot. Okay. And on this side, some intermediate samples, then here, who comes? X minus m from the left hand side, because m minus 1 samples, x 0, x minus 1, minus 2, so total m minus 1. So, after that, here we will have x minus m dot 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 dot. Okay. And then you carry out sample wise multiplication. Now, you see at nth point, nmth point, I have got data multiply, but next this block is meeting these zeros here, m minus 1, m minus 1 zeros. So, they do not contribute anything. Then again this with this, then again this block and this block, they multiply, but these are zeros. So, they do not these colors do not contribute anything. So, then again this, again here this block, there is data, but here you have a 0. So, they do not contribute anything, forget them. Then this with this, and these fellows get added, and if you add, what you get is the following: x 0 h n, then left hand side x 1 h n minus 1, this with this, x m, this is x m, not x 1, I am very sorry, x 0 x m h n minus 1, x 2 m x 2 m, next will be h n minus 2. So, this is n minus 2 actually, dot 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 n minus 2. Earlier I wrote from this side, so 1 2, but I am now coming from this side. So, let this be n minus 2 adjacent to this. So, x 2 m h n minus 2 dot 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 dot, and on the other side x minus m h n plus 1 dot dot dot. This is the summation. Okay. What is the meaning of this summation? You see, it is a convolution between whom? It is a convolution between a sequence between this and this, because what is this sequence? M times decimated version, right. So, this sequence here, if you call it u n, in fact, you can write as r, u r, because I am interested in finding out y at a specific end. So, u r is decimated version. So, 0th sample will be x 0, first sample will be not x 1, x 2, but x m, next sample will be x 2 m, next sample will be x 3 m dot 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 dot, and here you have got x minus m at minus 1, 0, 1, 2, 3 dot 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 dot, because decimated. So, x 0, then throw away the next m minus 1 samples, then take x m, that is the first sample, then again throw away the next m minus 1 samples, then next take next, that will be the second sample, and dot dot dot. That if you do, that is your u n. With that, if you convolve h z, what you have? This was your h, original h. Original h is not expanded version, this is original h. If you convolve these two, what will you get? You flip this to the left, flip this. So, what you get is x m on this side, x minus m on this side, x 2 m on this side, x minus 2 m on this side, and you have to find out the convolution now at nth index, okay, and you have to show this is same as this side. So, nth index means the flip side sequence will be shifted to the right by n. So, if it is nth point where I have got h n, then I have got h n minus 1, say h n minus 2 dot 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 dot. So, after you flip, x 0 will come and sit below x h n, so x 0, you have flipped. So, x capital M has gone to this side. So, now you shift means at n minus 1, x m will come, because after flipping x m has gone to this side, this has gone to this side, then you are shifting, and before x 0 here it will be x minus m, then x 2 m, this is at index n minus 2 dot 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 dot. Now, if you convolve, if you multiply this with this, what will you get? X 0 into h n, nth point, x 0 into h n, then x m into h n minus 1, x m into h m minus 1, x 2 m into x 2 m is at n minus 2, so at n minus 2 you have h n minus 2, so x 2 m into h n minus 2, x 2 m into h minus 2. On this side, this n plus 1th index, x minus m h, this is 1. Sorry, yeah, this is n minus 1, this is a, this sequence, this point is n plus 1. So, I will have h n plus 1. Okay. So, h n plus 1 x minus m, this, and so and so. So, this is a convolution, right. This convolution is this term, which I was getting at here. This was, these two are equivalent. What I did? I found out y n. What is y n? If it is nth, it is n into mth here, because this is decimated. And then I found out n mth sample by convolving this with this. This is the original x n. Okay. This is the original x n. But this is expanded version. So, expanded version is you start with original h, and then h 0 and h 1 between them m minus 1 zeros, h 1 and h 2 between them m minus 1 zeros, the expanded version. With that, if you convolve, okay, x n and find out the output at n m. How to do the convolution? Hold this one sequence, h sequence, expanded h version h e n as it is. Take the other sequence, there is x n, reverse it, that is flip it and shift it to the right by n into m, because I am interested in finding out n into m. So, n into m, x 0 comes. After that, x 1, x 2 dot dot dot, x m minus 1, they occupy this next m minus 1 points, then x m, and so and so. So, if you now multiply and add, these m minus 1 samples contribute nothing, because they find zeros here. So, this into this plus this into this, and then again this m minus 1 samples contribute nothing, because they find another m minus 1 zeros here. So, again this into this. This way you get this term x 0 h n, then x m comes, h n minus 1 from top. Okay. Then h n minus 2 if it is x 2 m. If it is h n plus 1, it is x minus m. These zeros do not contribute anything, these samples do not contribute anything. So, next is x minus m, then only that only finds x h n plus 1, here they are zeros. So, that is what I got, and this I showed is equivalent to this, because if you decimate x n by m, the sequence you get is x 0, then first sample is x m, not x 1, then second sample is x 2 m, because you are throwing out intermediate samples, m minus 1 samples, then third sample is 3 m dot dot dot, and this is your h z means original h sequence. Now, you convolve the two. So, you reverse this x and shift it to the right by n, x 0 finds h n, because they are located at n a. So, x 0 into h n, then x 1, there is no x 1, okay. X 0, x m was on the, after flipping it went to the left side. So, it has now come before to the left of x 0. So, this is x m into h n minus 1, because they are at n minus 1th point. So, x m into h n minus 1. Then before this who comes? This was went to this left, Okay, this went to -1, this went to -2. So, here it is after shifting x to m, this guy has come, that will find sample at x n minus 2, because that is where they are located. So, you have got x to m into h n minus 2 dot dot dot, and on this side before x minus m, that came to the right of x 0. So, if it is x 0, here is x minus m, but that is at the next point n plus 1th point, and here it finds h n plus 1. So, h n plus 1 x minus n and dot dot dot. So, that is you get this expression, right. So, this proves identity 1. Then we go to Nobel identity 2. Suppose there is a sequence x n, I first expand it by m, that is between every pair of samples I bring in m minus 1 zeros, then pass it through a filter of this kind. So, remember this is low speed, but here after introducing this m minus 1 zeros in between every sample, this is high speed. If the original time period was tau, between two samples the time period was tau, now it is tau by m here, and this filter is working at that rate. So, this is costlier side. This by this identity is equivalent to this, that first you convolve x n with just h z only, not h z m, so before expansion whatever it was. So, it is at low rate, filtering is done at low rate, which is less costly, and then again you expand by m, you will get the same thing. If you have y n, you will have y n here. Okay. This is another identity, this also can be easily proved. Suppose I consider this 2 is a v n is expanded version, and what is this filter? This is already expanded. So, this filter is h, you can call it h e z equal to this. So, impulse response is expanded version of this. So, h 0, then zeros, 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 m minus 1 zeros, then h 1, this is the mth point, 2 mth, here you have got zeros, h 2 dot 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 dot, on this side say n mth means h n 0 0 0 n minus 1 times m, then again 0 0 0 this is n minus 2 dot 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 dot. Okay. This is the filter, and after we expand x n also like this. In fact, instead of v n, let me call it x e n, because we already know how to represent what is the notation we adopted for expanded. So, x e n. So, do not call it v n, directly x e n. So, x e n also here have got x 0 dot 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 dot. Okay. Then x 1 dot 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 dot, x n minus 2, x n minus 1, x n. Okay, there are zeros dot dot dot. So, to convolve them, now I have to convolve them. I hold this as it is, flip this x sequence and then shift it to the right by any n, not necessarily n into m, any n. Okay. So, after you shift, see either small n could be 0, capital M, that is 2 m, okay. There is a multiple of m or not multiple. See, either you will be shifting, you want to find out y n for all n. So, n can be either 0, capital M, 2 m, 3 m, like that, the multiples of m or not multiple, intermediate points, right. Both the cases you have to consider. Suppose I consider first the case where n is a multiple of m, okay, say L into m. So, I have to shift it, okay. Say n m, I consider, suppose instead of n, n is n m, all right, n is n. So, I have to, if I shift it, if I flip it and then shift it by n say, x 0 will come here, dot 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 zeros will come, followed by, because I flipped x 1, then zeros will come, then x 2, dot 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 dot, here we will have x minus 1, dot 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 dot, and if you now multiply samples of this and this, what will you get? X 0 into h n, then zeros, zeros, m minus 1 zeros, m minus 1 zeros, right, because both are expanded by m. So, m minus 1 zeros. Why m minus 1? Because I am at nmth point and expanded n into m, followed by m minus 1 zeros on this side and this side. So, this will be n minus 1 into m, this will be n minus 2 into m, because that is why this is coinciding with this is coinciding with this is coinciding with this, like that, and this 0 block, 0 block, 0 block, 0 block. So, 0 into 0 contribute nothing. So, we have got x 0 into h n, then x 1 h n minus 1, x 2 h n minus 2, and on this side x minus 1 okay, h n plus 1 plus dot 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 dot, all right. So, at nmth position, what you have is this, at nmth position output is this, but what is the output? You see x, it is simple convolution between x n and h n at index n, isn't it? X 0, you know, original convolution, forget about these zeros, the zeros are not there, say original h. So, h 0, h 1, h 2 and x 0, x 1. So, this first sample, second sample, not mth, not mth. So, you flip it, flip this and take to the right. So, x 0 into h 0, x 1 into h 1, like that. Okay. So, at nth point, not nmth, nth point convolution between x and h is this, right. That means, after expansion, if I convolve the two at n into m, that convolution is original convolution before expansion of the two sequences at index n. On the other hand, if I shift not by nm, but say 1 less than that or 2 less than that, then x 0 will come under 0, this will come under 0. Okay. See, here I have shifted by nm, so x 0 has nicely come at nmth point, here it finds another non-zero fellow from here. But suppose instead of nm, I have nm minus 1 say. So, x 0 would have come here. So, this here if it is x 0, this finds a 0 here and this finds a 0 here. Then these zeros, this would have been 0, this is coming here. So, this 0 multiplies this 0 multiplies this sample gets multiplied by 0, like that. So, there will be total will be 0. So, similarly, if nm minus 2, nm minus 3, okay, like if you are not understanding, if I am delaying by say as an example only, say nm minus r can be 1, 2 up to say m minus 1. So, either nm minus 1, nm minus 2, nm minus 3, like that. Then what will happen? Earlier at nm x was coming, it will not go there, it will come here at nm minus r. So, I will have zeros, at nm this sample will find, this is nm, a 0 from here, this will find a 0 from here, this will find a 0 from here, okay, and this 0 block, after that there will be a sample, but that will find a 0 from there. So, like that if you see, it will be all 0, because either non-zero into 0 or again non-zero from here into 0, otherwise 0 into 0. So, that means this is what? If you see this, if you convolve the two like this, convolve the two, okay, and then if you convolve the two at nth point, you have got x n convolved with h n, okay, at nmth point. at nmth point output is, but if I do not take, as I told you, if I do not consider nm shift, if I consider less than that, like this, these points are zeros. This point output, as I told you, by this shift and all output is 0. So, you get 0. Then again, if you go to n minus 1 into m, here you will get again the same convolution. This is convolution at index n. This is again the same convolution, but not instead of n m, it is n minus 1 m. So, it is at index at n minus 1, like that. All right. So, that means x n h n convolved, x n h n convolved, this was giving n minus 1th output, this was giving nth output. So, it was n minus 1, it was nth, but now it is n minus 1 into m, it is n m. So, in between zeros have come up. That is why you are convolving. So, between nth and n minus 1th, you are plugging in these n minus 1 zeros, and so on and so forth. Okay. So, basically, this will be nothing but this sequence. This sequence. Okay. Why this sequence? As I told you that if your shift is n m, then what at index n you get, if n is a multiple of m, that is n m, then what you get, you are shifting, you are flipping this and shifting by n m. So, n m is here, it is multiplying h n. So, sorry, n m is here, x 0 is multiplying, this is flipped and shifted. So, x 0 h n. Before that x 1 was earlier on the right side, now left side. So, x 0 h n, then zeros, again in zeros, m minus 1, m minus 1, then x 1 h n minus 1, then again m minus 1 zeros, x 2 h n minus 2. So, you get this product x 0 h n, x 1 h n minus 1, x 2 h n minus 2 plus dot dot, and here x minus 1 h n plus 1, zeros into 0, no contribution. So, this is what you get. So, at n into mth point, this output is what? This summation. But this summation you will look at, it is nothing but convolution between original x n, original h n evaluated at n. So, 0 x 0 is multiplying h n. So, after flipping, it is x 0 is shifted by n times to the right. So, x 0 into h n and other samples also. So, this is linear convolution, original linear convolution between the two original sequences x n and h n evaluated at index n, that will come at n mth point. Similarly, if instead of n it is n minus 1 m, so at n minus 1 into m, by the same logic, output will be original convolution at n minus 1, because at n mth output is original convolution at n. So, at n minus 1 mth it will be output will be original convolution, linear convolution at n minus 1, and so on and so forth. So, that is why at n minus 1 into m output is original convolution at n minus 1. And then if I do not shift by n m or n minus 1 m or n plus 1 m, n plus 2 m, shift by something else, like say n m minus r can be 1, 2 like that. Then what happens, as I told you, that n m x 0 does not come, x 0 comes here, it does not come at n m. So, x 0 comes here at n m minus r, there it finds some 0 value. So, this into 0, h n on the other end finds some 0 value, then zeros 1 0 multiplies h n minus 1, then next data multiplies a 0 here. So, like that. So, 0 into data or data into 0 and 0 into 0. So, output gets zeros. So, you will have the situation for all intermediate points, this you can verify, all intermediate points between n m and n minus 1 m. At n m output is convolution, original convolution evaluated at index n. At n minus 1 into m output is original convolution evaluated at index n minus 1 dot 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 dot. So, that means original convolution at n, n minus 1, n minus 2. After that, between n and n minus 1 you fill zeros, n minus 1 zeros. Between n minus 1 and n minus 2 fill n minus 1 zeros, like that. So, that is the expansion and you get this. So, that explains that these two are equivalent. In the next class, I will explain its advantage. Okay, it's some example I will give where this is used. Okay, thank you very much.